Hello everyone, welcome to today's class, Organic Spectroscopic Analysis. In this chapter, we are going to learn where does infrared absorption come from, at what frequency will absorption occur, types of vibrational modes and number of absorption bands, absorption intensity, infrared absorption of organic compounds, and interpretation of infrared spectra. Infrared corresponds to the transition between the vibrational energy levels of a molecule, involving the stretching or bending of the bonds. For an organic chemistry, the region of interest for infrared spectroscopy is of wavelengths from 2.5 to 15 micrometer, which is normally expressed as the wave number range from 4,000 to 600 cm per particle. Since this is the region in which the most diagnostically useful vibrations occur. This is the example of the typical infrared spectrum. The ordinates is linear in transmittance. The abscissor is linear in wave number. Now you may wonder where infrared absorption comes from. The absorption of infrared radiation by a sample is due to changes in the vibrational energy states. The pattern of absorption as a function of wavelengths is called an infrared spectrum. As a polar molecule, such as CO, vibrates, a regular fluctuation in dipole moment occurs, and a field is established that can interact with the electronic field associated with a radiation. If the frequency of a radiation exactly matches the natural vibrational frequency of the molecule, absorption occurs. Similarly, the rotation of asymmetric molecules around their centers of mass results in a periodic dipole fluctuation that can interact with infrared radiation. Dipole moment change during vibration. When molecule compressed, dipole moment decreased. When molecule stretched, dipole moment increased. Infrared spectroscopy can be divided into far, mid, and near infrared. Since the fundamental frequency vibration is the strongest absorption in the infrared spectrum, and most of the fundamental frequency absorption bands of organic compounds and inorganic compounds appear in the mid-infrared region. The near-infrared region is most suitable for qualitative analysis, such as qualitative analysis and structural analysis of organic compounds. With the advent of Fourier transform technology, the application of this spectral region has also begun to be useful for microspectroscopy analysis of surfaces and analysis of solid samples. At present, in the research of absorption spectroscopy in the mid-infrared region is the most mature, and a large amount of the data has been accumulated. Therefore, it's the most widely used spectroscopy method in the infrared region. The infrared absorption spectroscopy generally refers to this range of spectrum. The electronic interactions between atoms in molecules provide a binding force and a restoring force often compared to springs. Even having the quantized nature of molecule vibrational energies considered, the following equation develops. A disturbance of one of these masses along the axis of the spring results in a vibration called a simple harmonic motion. Its frequency is given in this equation here, where K is the force constant, indicating the strength of the bond. M1 and M2 are the masses of two atoms. In the mechanical mode, the energy curve takes the harmonic form. In a more accurate quantum treatment, the energy curve must take the anharmonic form. Note that harmonic and anharmonic curves are nearly alike at low potential energies. This fact accounts for the success of approximate methods described. Energy difference in the adjacent levels can be calculated as the following equation here. And the stretching frequency can be calculated according to this equation. Let's look at this example. Please calculate the approximate wave number of the stretching vibrations of a carbonic group. The atom mass and force constant are given as follows. Please write down your answer in the discussion section after class. Molecular vibration modes include stretching vibrations and bending vibrations. Stretching vibrations have symmetric stretching and asymmetric stretching. Binding vibrations include scissoring, rocking, wagging, and twisting. Usually, bending vibrations have lower frequencies than stretching vibrations. These are the wave numbers of scissoring, wagging, rocking, and twisting vibrations of methylene. Water molecules have 3 vibrational modes, including symmetric stretching, asymmetric stretching, and bending modes. The traditional IR instrument is dispersive infrared with an infrared source, sample compartment, monochromator, and infrared detector. High-resolution infrared instrument uses the Fourier transform infrared instrument. Samples for infrared spectroscopy can be prepared in a number of ways. As for solids, solid samples can be grounded with potassium bromide to form a very fine powder. This powder is then pressed into a thin pellet, which can be analyzed. Solid samples can also be dissolved in a solvent such as chloroform and the solution placed onto a sodium chloride plate. This solvent is then evaporated off, leaving a thin film of the material on the plate. A mole of a powder with hydrocarbon oil can be also placed between sodium chloride plates. For liquid samples, the easiest way is to place 1 drop of sample between 2 plates of sodium chloride, forming a thin film. Solutions can also be analyzed in a cell made from sodium chloride or other infrared transparent material, which can be filled with liquid. For infrared windows, the sample cell window must be infrared transparent. For gas can be directly introduced to the sample inlet. This picture shows the dye for preparation for potassium bromide disc. Preparation of infrared samples as potassium bromide disc are as follows. Infrared plates can be rinsed with acetone and gently wiped dry. So that's today's lesson for Introduction of Infrared Spectroscopy. Hope you enjoy it. Thank you for watching. Goodbye.